My name is Braylon Nix, and my major is electrical engineering. So, my presentation is about how quantum computing and electrical engineering intersect, both in terms of how quantum computing can benefit various subfields of electrical engineering, and also how electrical engineering itself is essential for the development of quantum hardware. So, before diving into some electrical engineering aspects, I'll talk a little bit about the motivation for why quantum computing matters for electrical engineering. Much of this we've already discussed in the class previously, but the end goal of why quantum computing matters is that it offers potential speed ups in very hard problems dealing primarily with optimization, simulation, cryptography, communication, and other areas, a lot of which are very relevant to the fields of electrical engineering. Quantum computers, however, are not built in a vacuum. They are built using some combination of microwave engineering, materials science, control systems, photonics, and other areas of expertise, depending on the specific implementation of the quantum computer itself. Electrical engineering kind of sits in the middle, where quantum computers need electrical engineering in order to exist fundamentally. And once they do, they can help solve some of electrical engineering's more difficult problems. So, from an electrical engineering implementation perspective, qubits can be thought of as a controllable analog signal, so that instead of storing a 0 or 1 like classical digital computers, it stores a continuous complex amplitude. Uh, Physically, whenever we apply microwave pulses, lasers, etc., as different quantum gates, basically what that's doing is some type of controlled mathematical rotation, very similar to how classical resonator circuits work uh, in electrical engineering using capacitors and inductors. So even though quantum mechanics itself can be weird and complex and unintuitive and hard to understand mathematically, the control side of qubits is very electrical engineering friendly. So, some quantum hardware contributions from electrical engineering. A lot of the progress in quantum computing is actually engineering progress. Superconducting quantum computers, for instance, need precise microwave pulses, ultra low noise amplifiers, signal routing that happens at millikelvin temperatures, very close to absolute zero, and shielding from interference to stop decoherence of the qubits. All of these are very electrical engineering heavy topics. Google, IBM, and Rigetti all have entire teams of electrical engineers who design the various cryogenic control electronics and microwave systems that help to keep the qubits stable. One of the biggest intersections between electrical engineering and quantum technology is in quantum communication. We already use optical fibers, detectors, and modulation techniques in modern day fiber optic internet technology. And quantum communication just pushes this to the single photon level. Electrical engineers design these detectors, the timing circuitry, and the various protocols that make quantum secure communication possible. A lot of the electrical engineering problems that we have today are huge optimization tasks that deal with power flows, network routing, various control decisions, and complex circuit layouts. The quantum approximate optimization algorithm, or QAOA, and the variational quantum eigensolver are some early quantum algorithms that could give speedups for these tasks. Physically, the technology is not quite there yet to be realizable, but multiple papers have been published that show promising results for power grid optimization and signal processing using small quantum circuits. A couple of these are Q grid quantum optimization for the future energy grid by Bleninger J et al. In 2024. And this year, a paper titled A Review of Quantum Computing Technologies in Power System Optimization by Chun Wai and Vu T in the PNNL report. And I'll click here to show some of my code. Essentially, it's very simple, and the max cut and graph optimization were talked about some both by Gracie and Roland in their presentations on Tuesday. But specifically, if you use these graph optimization problems, what we're doing is we're starting with a very small graph made of just a couple of nodes, and we turn that into a Hamiltonian, which basically encodes the viability or how good each possible solution is. And the QAOA builds a quantum circuit that tries to explore many solutions at once. Here's a drawing of the quantum circuit in the code on Qiskit. And first, as you can see, all of the qubits are put into a superposition using Hadamard gates, and then they apply various C0 operations. And these are called cost operations or mixer operations, depending on the type. And the algorithm repeats a couple of steps each time. You can increase the depth of this multiple more times, which will increase the accuracy of the simulation. But ultimately, if you were to build that in a physical quantum computer, that results in more circuit complexity, which we just don't have the capability of right now. But what this does is a classical optimizer adjusts the circuit angles, which you can see here, the small gamma and beta that are kind of subscript under these RZ and RX gates. Those are parameters that act sort of like um, knobs that keep tweaking the quantum measurement outcomes to get a better solution. So the algorithm ultimately reports the best parameters with the lowest energy in the Hamiltonian, and that lowest energy represents the best solution found by the algorithm. So it's able, the quantum circuit part of it is able to explore many possibilities at once. And then the classical optimizer part of the circuit tunes it, so to say, to steer it toward the best answer. For the and for this one node, I actually just made it two nodes, and so you can see that whenever it runs the probabilities, essentially it's saying that 0 to 1 or 1 to 0 are both 50%. They're both equally short solutions with this one node graph. For the VQE, that was a little bit harder for me to understand, but basically, it's describing. You can describe a small physical system like an electronic circuit using a Hamiltonian, and then you build the that circuit using adjustable parameters, and it's sort of like a neural network. And then the quantum computer evaluates the energy of the system for a specific set of parameters. And then it also has a classical part to the algorithm as well that adjusts the parameters to minimize the energy. And then the lowest energy that the algorithm finds corresponds to the system's uh, ground state, which is also highly useful in chemistry and materials science. So, quantum computers can simulate quantum systems themselves much more efficiently than classical computers. And this matters for electrical engineering because semiconductor devices, new electronic materials, and nanoscale effects are becoming harder and harder to model classically. So, quantum simulation could eventually help design better transistors, superconducting circuits, or even things like new battery materials. So, what's realistic today? Right now, we're still in what researchers call the NISQ era of quantum computing. This stands for Noisy Intermediate Scale Quantum Computers. This essentially means that we cannot feasibly run huge algorithms yet, but we can do some important things such as demos of optimization problems, like the two algorithms shown in the code before. We can run small chemistry simulations, and we can build real quantum communication systems. Most of the progress right now is actually required in engineering so that we get better qubits, cleaner signals, and better control hardware. So, what are some topics that electrical engineering students should learn about in the future if they want to work in the quantum computing industry? Uh, Some of the important ones include RF, radio frequency or microwave engineering, control theory, materials science, semiconductor devices, cryogenic electronics, which that's primarily a graduate school only topic, embedded systems and FPGAs, and photonics. So, to wrap up, electrical engineering itself is deeply involved in building quantum computers, no matter the implementation type. And at the same time, quantum algorithms show exceptional future promise for solving electrical engineering problems, particularly in optimization, communication, and simulation. And in the future, I think that more electrical engineers will be essential to making quantum computers